So there's three things affecting the resistance of a wire: length, cross-sectional area, and the material that it's made of. And in the chart, if you take a look at the chart real close, you see that the one that has the least resistance involved, or least resistivity, which is related, as you see, a direct relationship between the two, is silver. And they don't have gold on there because no one uses gold, but if they could, or if they would, it would be even better than silver, I hope. So, now, the fourth thing that has an effect is temperature. And temperature is rather interesting. One of the things that exists now that we haven't had when I was first into the science world was something called a supercomputer. Now, a lot of people hear the term supercomputers because the weather department uses supercomputers, and a lot of research groups around the world use supercomputers, but they don't really explain what a supercomputer is, so I'll do a quick job on that. A supercomputer is one in which the resistance within the wiring of a system is minimal, practically zero. Now, the problem with a computer that does a lot of things at once is that it creates a lot of heat. There's a lot of friction. Resistance is friction of electrons, and friction gives off heat. And so you have a tremendous amount of heat coming off of these computers that do these dynamic calculations. The supercomputers now do trillions of calculations in a second. That releases a tremendous amount of heat. So what they need to do is to cool that thing down as low as they can. And they were using liquid helium for a while. Of course, helium is hard to get because it's not found on Earth in the atmosphere, but it's found in radioactive rocks. They're trapped in that, so they get them from that. So that's a pain. So the big engineering feat that has been done recently is they were able to establish alloys of wiring that gives off very little heat. That's a big deal. So the higher the temperature, the more resistance you're going to get. It's basically what this is all about. So we have another factor that we have to take into consideration here, because again, it's a direct relationship between resistance and temperature, is this alpha. This is the first letter of the Greek alphabet to counterbalance the omega for the resistor, which is the last letter of the Greek alphabet. And this is called the temperature coefficient of resistivity. So this is how we correlate all that in there. So rather than develop a new series of equations together with all four factors, we leave the three factors that we had before. That's the material, the length, and the cross-sectional area. And we simply find that first, and then we take into account the temperature with this equation right here, where this means the resistor, or resistance, is equal to the original resistance in the problem that we dealt with would be 0.0180 amps, times this correction factor that increases the temperature, change in temperature, with the factor called the temperature coefficient of resistivity, plus 1. So this is 1, which means it's going to be this value of the original resistor plus this factor multiplied by that on top of that. Now, if I were to multiply this across here and use the distributive property, I get RO times 1, and this again is the original resistance, so RO times 1 is RO, and RO times this is this complex system here. Then I subtract the RO over here to leave this right here in that form, and R minus RO, which is final minus beginning, that's delta R, and it's going to equal to RO times alpha times delta T. These are the two equations you're going to use. This is showing the derivation of this. If you want to find the resistance of a system at a certain temperature, this is the equation you use. If you want to see how the resistance changes, you could do this and subtract from the original subtract with the original resistance, or you can just go ahead and do this equation right here, which tells you what the change of the resistance is going to be. All right, so I gave you an example of this. In the previous example, when we had that resistor of 0.0180, which we are now designating as R sub O, and it heats up from 20 degrees to 30 degrees, what is the new resistance? What is the value of the resistor in this particular system? So we look up this for copper, it is 6.8 times 10 to the negative third degrees Celsius to the negative 1 power. Again, this is a constant, so you got a goofy label for the constants. But now you have something to plug into the equation. This will go in right here. 0.0180 times 1 plus that alpha that I just gave you times the change in temperature, which is 10 degrees. Add and multiply that together, and you get 0.0192 ohms. So that's the relationship we have between current, voltage, and resistance. So, and how we can predict resistance of wiring. So, our practice problems on your script. There are 5 sets of questions. Have fun.